Now, this is a spherical lens that's a sphere. Let's make a spherical lens which is a section of a sphere, but not in itself spherical. And I'll show you how we do that. We do that with my ring. I just happen to have this ring. It's 50 millimeters in diameter. It's 8 millimeters thick, okay? And it's made, this one happens to be made out of a special material. It's called Monel. It's a nickel alloy, corrosion resistant. And I'm going to use this to demonstrate spherical lenses that are both positive lenses and negative lenses. Lenses that have convex surfaces, lenses that have concave surfaces. Here we have my ring. And I'm going to use the two-dimensional beaker. Got to open up the slit here with my finger because this happens to be a cantankerous bag. So I'm sliding. Okay, so there, my two-dimensional beaker is over the ring. And now I'm going to pull the two-dimensional beaker off, also known as a plastic bag, while I squeeze it, and I'm going to put some water on that ring. Okay, look at that. Remove a little water. Oh, look at that. Oh, perfect. So what we have here is a double convex lens. And this lens is positive. That means it acts as a magnifier. And convex means it bulges out. So each side bulges out. And it's maybe a centimeter, maybe 10 millimeters, 12 millimeters thick in the center. And I'm going to kind of get behind it. And Andre told me what I need to do in order to show magnification. Okay, and this lens, because it's not a complete sphere, has fewer aberrations than the lens that was a complete sphere. This one is still considered a spherical optic because the surface is formed in the shape of a spherical surface, but it's truncated. It's not a complete sphere, and it has fewer aberrations, even though it still doesn't make a perfectly fine image. Okay, how's the ship's log look? I'm gonna remove more water from this lens to the point where the meniscus on each side is almost parallel and the same thickness as the ring. And this, look what happens when I do that. So I'm sucking out the water with my syringe. And now I'm just looking at this on the side. Okay, it looks like the two sides are pretty much plane parallel. And now it's just like a piece of glass. There's no real magnification in this. Well, what we're doing now is making a concave lens, a double concave lens. This is referred to as a negative lens. It makes things smaller instead of bigger. So what I'm going to do now is remove more water and make this into a negative lens where the surfaces are concave. And it's concave now because the surface of the water is pinned to the thickness of this ring. And I can remove the water and the surface is still pinned to this outer edge. And if I remove water so that there's less volume in here than the cylindrical volume of the ring, the center gets sucked in and it makes it into a negative lens. So let's see what this looks like now. Oh, I can tell right now This is a negative lens. Look at that. I can see Andre running the camera, and he is small.
Oh, yeah.
And it's smaller, correct?
Yep.
Now there's a whole series of lenses that are really thin, and they're called meniscus lenses. They're the kind of lenses that are used to make your eyeglasses. They're all referred to as meniscus lenses. But I think this adds a new twist to optical lens making, because this lens, you could say, is really a meniscus lens. That concludes our little demonstration here on the International Space Station using water and wire and this little ring to demonstrate a little bit about spherical lenses, and spherical lenses that are really not spheres but sections of spheres, and what happens with a positive lens that's convexed and a negative lens that is concave. It is good. Okay, so I'm upside down.
Absolutely.
Okay, now I'm going to start sucking the water out. I'm going to stay in this position. And we're going from a positive lens into a negative lens. And now I'm right side up.
Yep.
And I'm smaller than life.